All right, everyone. So now what we're going to do is we're going to actually create our to put ourselves in the right pole position to meet our design specifications. We're going to do control via root locus, and we're going to use this lead compensator, and we're going to have an open loop transfer function. So this is our transfer function that we're going to be working with. So we can see a couple things already. So I can go ahead and we see we have 4 poles. We have 1 at the 0. We have 1 0. So n is equal to 4. We also will have number of zeros is 1. 3 branches, n minus 1 will basically asymptote or approach infinity. 1 branch will terminate at a 0. And the intersection of the real axis for asymptotes we see is at minus 4.5. We can calculate those departure angles as such, just using our equations we've developed before. We can also look at those angles of departures for minus 8. You can see 0, 0, and here. We can also probably do some break-in, breakout rules, but we'll actually look at that here. So let's see what we've got here. So how many are going? We said 3 go to infinity, right? So we can see here, here, and they're going to asymptote to it. This one is not going to go to infinity, right? Starts here, travels until it hits essentially that 0. I wish we can zoom in a little bit more or expand out. Maybe I can just reduce the K here, but you're going to see I'm going to actually have to deal with it a little bit further in a second. Yeah, here we go. We can see that 0. So we can see here it's going to approach and terminate here. That's our 1. This goes to infinity, and we can essentially see that angle, right? And so actually if I increase now to 1,000, so you can see 1 is just setting 0, and the other one is going to basically that departure angle will be here. 0, 0. So actually we can see at minus 8, which is over here, goes to minus 180 here. At minus 6, hopefully we have basically that 0. At minus 1, it leaves here at 0. And then at that pole here of 0, it goes at that. Where's that pole? We don't have a pole at 0. Actually, we do have a pole at 0. Excuse me, that 0 should be at minus 1.5. So the pole here at 0, or minus 1 is going to go to the 0 to the right, just like that one goes to the right, and then this one goes to basically 180. Could be like minus 180, just to be consistent, but we get the picture. So that's the angle departure, and then you see the kind of like that 60-degree, 60-degree angle that asymptotes. And there, we can kind of see where we're going there. But anyways, that's more analysis than we need here. The key thing that we're going to see is, all right, so we've designed essentially that system. We've analyzed, and we can kind of see, the centroid of the asymptotes. So basically, this is going to asymptote and cross our axis at basically minus 4.5. Makes sense. Like, look at, if you kind of follow along with that angle, you kind of see at infinity that angle kind of sharp, and it might intersect essentially there. So, and we also can see that center, and then you can see essentially the angles there as well for the branches that depart from here. So at those angles. So minus 4.5, you get this, you can get this, and then I'm trying to think of where the other one goes. Almost 300, which is basically flat there. But anyways, from that minus 4.5. Great. So now what we're going to do, so we are now going to look at how do we kind of interpret it. So we have now this 0 here. We have a pole that basically keeps us in basically that lead localized. And so now for some values of K, we can achieve and actually fit in that zone. And we can essentially see these pole regions, and you can kind of look at depending on some of the K values, where we're sitting at. Now, this is a little bit, I'm going to have to fix this later. But we can see this here. If I were to, or if we were to, put this in our pole region now, we can see, okay, where we're sitting for certain values of K, right? So, for example, I can take, I don't want to do poles per se. Actually, we can see already for any value of K, or actually, we see where the values of K are changing, but we can sit in some of these regions. So we can kind of see how the system will change, or how some of those values can be interpreted. So now we can see that our root locus, we're sitting in this region where we can be stable, and we can hit some of those metrics. So that's really, really kind of important and critical. So you can kind of see here and vary. So right here, we're looking at, okay, K value of 1, K value of, and we can kind of adjust that here too. So for example, if we just look at, let's say we're just even at a value of 1. So let's make it 10, just so we can kind of see some things. But we can kind of put this here. So there are poles and behaviors that put us in that regime. And we can look at the system response, and we can see this is it's a pretty nice response. And we can calculate those values, and we can ensure that, again, we are indeed hitting them. And actually, for any values of K greater than 0, we can achieve essentially this, because we have those poles that land in those regions. So you can calculate it, you can confirm, and we can visually see that here. So it's a good, fun, productive analysis that makes sure that we're landing in the right region. Fantastic. If you want to improve the steady state behavior, you can add an integrator term, and that's essentially that's how it goes. We can look for an example of this with integral control as well. So if we look at this system with an integrator control, we can see we have that pole at 0. We have kind of this complex pole. We have a 0, and we can look at and calculate similar centroids and values as well. But we can now do this essentially with our Ruth table. So let's go ahead and let's walk through this analysis. So with integral control, I'm going to go over here, and let's go ahead and let's look at this system. So we are going to take now our GS simple equals this, full simplify, and we can basically expand out this, which is what we've already done here. And now in our Ruth table, if we want to see and make sure that, again, what values of K, and put some bounds to make sure essentially that our system is going to be and maintain and not become unstable. And we can double check essentially these values as well in just a bit. But we can kind of go ahead and see, you can see it here. So from our Ruth table, our condition is just simply that it's going to be K has to be greater than 0. That's one condition. And we need to make sure K has to be greater than 0, and K must be less than 3. So if we're in that regime, we're completely okay. So we can do our transfer function model. We can do GS simple. And we can make sure, again, how many poles do we have? We should have 3 poles. So we should have 3 branches, and we see we indeed have those. And you can kind of see we're pushing us into kind of an unstable point, right? We're in that right-hand plane. So we need to make sure that if I'm between 0 and 2, even then it's looking like you can kind of see where we're headed, which is not particularly safe. So we need to make sure, 0 and 1 would be good. So you can kind of see, and again, it's just kind of showing you where the value is, right? And it's showing you where essentially you're going. So for example, if I put us at 4, we can see here, why is our K value? Oh, it's sometimes it does this. We need to have this simplified. And then I want to expand out here. Let me see if we can do. Let's see if that gives us any further issues. I see. No, excuse me. We're doing open loop transfer function. So this is for the closed loop transfer function if it was there. So our GS simple will just be CS times P of S. I always think about closed loop, but open loop gives us a little bit nicer and gives us a little bit easier kind of tools to work with. And then I want to expand all here. And then I think this is going to give us a different little answer and response. So exactly. So now we're going to see, oops. And that's why it's always good to double check and visualize this, right? You can kind of see what's happening. So I'm going to go 1. But yeah, if you're closed loop, then you'd have to essentially analyze that Ruth table and exactly what we said here, find those values. But if you wanted to look at it here, you can kind of see that. So just different behaviors. You wouldn't even have to, but actually it's good to practice. Let's do 1, 1, 3, 0. So we're stable here, and we can kind of prove that with this value here. So really here, but you can still, actually, that's kind of an interesting point. There's still values of K that can get us in trouble here. And you can analyze that from that closed loop, essentially, behavior of that system. So if you have over 1 plus CS times PS, now we're looking more complicated, and we can kind of expand out here. And then we can get 1, 1, K plus 3, 2K. And there we go. And then now what you end up with is this. Similar, you kind of see the angle sharpen, and then we can kind of see, okay, what's happening in that system, and how to treat it. So you can kind of see where we're at. But yeah, so we had to be careful, make sure that your stability is bounded, and that, again, we're going to behave well. So yeah, that's effectively what we've got. Now, next time we're going to actually calculate what is the critical gain for stability and kind of transition our way into some frequency analysis. So see you in the next video. Thanks. Bye.